Right, we're good. Can you let me know when you see my screen? All good?
Yes.
All right, cool. Hi, everyone. Thank you and welcome to 2020 APAC Groundbreakers Virtual Tour by APAC OEC. This year, our event would be the biggest one ever done with 174 sessions, including normal sessions, workshops, and hands-on labs from 123 different speakers over 11 days. Also, it would cover sessions on different 4 languages. Please remember to register as many sessions as you can, and all sessions would be available to replay as many as times you want to 2 weeks after the initial session date and time. You can also interact with the speaker at any time during 2 weeks by posting questions or comment directly in the playback session page. And with that, we would like to thank you to all the Oracle user groups and Java user groups that made this event possible, and also to our sponsors, Oracle Groundbreakers, Breakers, and CloudDB. Now, for today's session, we have Connor McDonald presenting building successful applications on the autonomous database. Please feel free to write questions at any time during the session at the question and answers tab at the Zoom webinar, and the speaker would be answering them at the end of the session. If you have any issues during the presentations, please feel free to contact me at any time on the chat tab. And now, without any more delays, I would like to leave you with this amazing session by Connor. Connor, over to you. You can take out the slideshare.
Thank you. Hopefully you can all hear me and hopefully you can all see me. Let me share my screen and we'll get straight into it. I'm quite excited. This is finally a webinar I can give in my own time zone. It's very exciting. Okay, so let's... Now, hopefully you can now see my slides and see me. Feel free to minimize me if you'd rather not see me. So my name's Connor McDonald. And this is how you get in touch. I love talking technology, and probably the best way to get in touch with me is probably on Twitter. That's my Twitter handle, but I also run a blog and a YouTube channel for tech content. So hopefully I cover off all the bases there. If you just want casual tech chat, hit me up on Twitter. If you want more long form stuff, go to my blog. And if you're more of a video focused person for your tech education, then yeah, please go to my YouTube channel or go to all three, obviously. This is what I do most of the day. I look after the asktom.oracle.com website with my colleague Chris Saxon. And seeing as you're on a webinar, you obviously have an interest in these style of events. So I just thought I'd do a quick shout out there that we have a thing called Office Hours. It's been going now for 2 years. Literally various product managers inside the Oracle organization do a 1-hour webinar at least once a month. So across all the product managers, we have had over 400 of these sessions in the last 2 years. So we're going to talk about successful application development, particularly on the autonomous database. Now, before we begin, I just want to say one thing. You've no doubt seen this graphic in various shapes or form over the past 9 to 12 months. I just put it up there just to say, obviously, we have great communities here, depending on what user group, etc., you're coming or attending this event from. But obviously, communities only work if we actually have a community, as in people. So please follow your local bylaws, stay safe, stay healthy. One day again soon, hopefully, we'll be doing face-to-face events. But obviously, that's only going to work if we can ride this particular period out. So please stay healthy and please stay safe. Let me start with a little bit of controversy. It's all about fundamentals. Obviously, application development over the years has got more and more and more complex, but I wanted to focus purely on fundamentals today. And let me just try to justify why. The reason is pretty simple. I've put a little database there on the screen. It's tiny. Now, why is it so small? Obviously, the database is core to just about everything we do when it comes to building applications. This is still true, but nowadays in modern application development paradigms, it's a bit more like this, in the sense that the database is still at the heart of everything, but we're adding more and more and more layers on top of it. But it doesn't really matter how many layers you have, because the database remains at the core. In fact, your data remains at the core. SQL Performance is pretty much the core to everything. If access to data, even if it wasn't via SQL, if access to data is slow, then everything else suffers as you go further and further outside the stack. So it's about those fundamentals that is critical. Now, don't get me wrong, I work for Oracle and we definitely push hard on our marketing messages about our autonomous database in terms of self-managing, self-healing, etc. And it's true, it's a very, very impressive piece of technology. And people think, well, surely I don't have to worry about anything if I'm running on autonomous database. Well, this is true, but here's the problem. And autonomous is running on our most advanced hardware there is. It's running on Exadata gear. But here's the problem. The problem is us, the development community. And let me take a small digression here to try justify that statement. Let's have a little bit of history now on database servers or servers in general. Not too long ago, maybe let's go back maybe 20 years. If you ever went to college or university or studied any kind of course on computer internals, they all looked like this. You had a CPU, you had other bits for I/O and memory, and you had this thing in the middle called a bus. In this diagram, it was called the FSB, which stood for front side bus. And any access to anything always went through the bus. CPU talking to memory, CPU wanting something from I/O. You put a message on the bus, and the bus would respond, and you would get that information. What it meant was it didn't matter how fast CPUs got, and CPUs were, as you know, just doing this the whole time. They were stuck because they were limited to what the bus speed was, or how fast we could do interrupts and servicing requests along the bus. This was a great time to be a developer, because in those days, it didn't matter how good you wrote your code. Some servers, in fact all servers, simply couldn't do the job. It didn't matter how fast the CPU was, they were held back by the bus. And so as a developer, you could say, look, my code is great. It's the server. The server technology just isn't up to par. And that beautiful time to be a developer where you could blame the hardware, these guys ruined it for everyone when they came along and invented a thing called hypertransport. And that was a different way of architecting servers where what would happen is you could now have each CPU could have direct access, not via a bus, access to a portion of the memory on the server. And furthermore, you could access other parts of memory by going over a very, very fast interconnect called a hypertransport. You had memory access direct from CPU. Intel saw this and thought, that's a pretty cool idea. And you may have heard of this thing called the Nahala Architecture, or the modern or quick path interconnect, we call it, all the modern stuff that Intel's chips nowadays all really started their bloom in terms of performance around 2007 with the same kind of concept. CPUs accessing memory directly and incredibly fast. Why do you care? Why did I join this SQL webinar to get a lesson on server fundamentals? The reason you care is this. It's a sad time to be a developer. You can't blame the server anymore. Servers are ridiculously fast. If you can't get the levels of performance that probably 99.9% of all applications out there need, then really it's on us. Now, rather than just pontificate here, I thought I'd show you a very simple demo of how stupidly quick computer hardware is nowadays. So I'm just going to run this thing called PK demo. Now, all it's doing is firing up SQL Plus here. And you can see I'm running on version 19 of the database, and I'm running on this machine. I'm running on basically a laptop here. So it's a $1,000 laptop. It's a few years old. It's hardly what you would call server-grade technology. I've got to pause here. What it's about to do is launch 10 concurrent SQL Plus sessions, and each one of them is going to be doing primary key lookups as fast as it can. So you'll see them all start to come flying in. And all I'm doing is if we flip, doing 40,000 times 10,000 primary key lookups. So 40,000 primary key lookups. Now, if we look at the results here, and don't get me wrong, we also got a Zoom session running at the moment, and me, chatting away. I'm doing audio and video. Yet each session, 53,000. What do we got here? 53,000, etc. There's 10 of them. They averaged about 50,000 plus primary key lookups a second. So that's 500,000 SQL statements per second. Now, people say, but that's different because in the modern days, everyone's got a mobile phone device and, the volumes of data and the frequency of data is just out of control. That might be true for a tiny percentage of people, but the vast majority of people don't need that kind of scale. You don't have to race out and think, oh, we have to install Mongo or Cassandra because a relational database won't be able to cope. That is simple fiction. If a $900 machine can do 500,000 SQL statements per second, rest assured the vast majority of your application requirements are quite happily served with a relational database. If you can't get that kind of performance, then yes, maybe those more esoteric kind of models like Mongo or Cassandra or Oracle's own NoSQL thing might have a place for you. They might have a place, but it's at the very extreme end of performance. One of my favorite quotes is this guy, Ted, who said, the sooner you realize you're not at the scale of those very few enterprises that need ridiculous sort of levels of clustering and NoSQL infrastructure, the more you can get down to actually getting your work done. So if you're not getting 500,000 queries per second, and yet you've spent more money than I have on a $900 PC, what's going wrong? What's holding us back if we're not seeing those kind of behaviors on our much more expensive servers? It all comes down to you're doing too much work or you can't get work done. So we're going to focus on the importance of SQL fundamentals from that perspective in terms of what could possibly be holding us back or stopping us from getting the levels of performance that we'd like to achieve. Now, SQL is like any language, obviously. You think about C or Java or anything, they all pretty much have three fundamental tasks. You have to compile it. Obviously, you have a language, you write code, and you compile it. SQL's a bit different because you compile it on the fly. You present it to the database and it's compiled right there and then, as opposed to in advance, like other languages. But then obviously you run it, just like any language, like C or Java, and then something happens. You don't run computer languages just for the sake of running them. Some consequence comes out of it. You either get some sort of result or you might need to store those results. And SQL is the same. Compile it, execute it, do something with the results. For successful applications, obviously, and this is just common sense, you would need to compile it fast, you would need to execute it fast, and do something with the results fast. If you can tick those three boxes, obviously you've got a very fast application. And that's it. It's pretty simple. All this, talk about complexity in SQL really comes down to those three things. Now, what everyone talks about, and I'm not being critical here, it's just a very common thread, is this. We forget about the compilation stuff. We forget about the storing and retrieving results, and everyone focuses on the execution part. You've seen countless SQL tuning talks, execution plans, explain plans, etc., doing tracing. We focus very, very heavily on the execution part of SQL performance. So rather than do that, this session is going to do the opposite. We're going to focus on the compilation phase and what we do after our SQL is executed. And if we can get those two fast, then we're well on the way to having great applications. So part one is compiling SQL and how to compile it fast. Now, let's get some common terminology here. If I give you the following code snippets on screen, so I've got an anonymous block here, I've got drop table, I've got delete from my table, select star, and begin an anonymous block. Which of these would you say are cursors? Now, obviously that one is because the word cursors sitting in there. This one probably is, we call it an implicit cursor, but how about these other ones? Well, in reality, they all are. From a coding perspective, we often write cursors, but from a database perspective, a cursor is simply an operation that requires some memory. So from the database perspective, everything you ever do pretty much is a cursor. And a cursor really has three phases, even from the database's perspective. We have open, process, close. Open simply means I need some memory. I need you to give me a pointer to some memory so I can use it for working. Then we process something using that memory. We might ask for more memory, we might shift stuff back and forth, but the processing part is getting work done. And closing is simply telling the database, I'm done, here's your memory back. The problem is the moment you want to access memory on a database server, because lots of people want to do it at the same time, it requires controlled access. And a quick primer on database memory from an Oracle database perspective's point of view. Almost all of Oracle memory is doubly linked lists. It's whenever I see this diagram, I wish I'd listened a bit more carefully in college or university. We did stacks and queues and first in, first out, and etc. But a lot of Oracle memory is doubly linked lists, links that go backwards and forwards to link together blocks of memory. Now, I'd like to present a metaphor here to help explain how we access memory in the Oracle database. Do you remember when we used to get together in social outings? It seems so long ago, doesn't it? But we used to go to pubs and bars and concerts and stuff like that, and we generally had a really good time until one thing happened. We needed to use the restrooms, because that's always just a nightmare when you go to a large-scale public event. And a toilet is actually a fairly complicated thing. Bear with me here. Follow the metaphor here. It's a fairly complicated thing. And therefore, what you don't want to have is lots of people competing for it. If you have two people sharing the resource at the same time, things get a little bit awkward, as you can see here. So what is a toilet at a concert? It's a limited resource. A lot of people want it, but if you access it concurrently, it's a little bit uncomfortable. And it's a complex system. And it's actually the same with Oracle memory. How do we solve the toilet problem? Well, what we do is we have introduced a very simple mechanism that everyone understands that controls access to the toilet. We call it a latch. And guess what? In Oracle memory, we do the exact same, even with the naming. We call them latches. So here's my complicated memory structure in the SGA. It's a doubly linked list. To protect that when more than one person wants to access it at the same time, it's protected by this little lightweight piece of memory called a latch, just like your public toilet. So the first thing you need to do, just like the toilet metaphor, is you need to get access to the latch. If I have access to the latch, now I'm allowed to use the complex system. I'm allowed to access and manipulate memory. And then when I'm done with that and I'm finished, I then exit the toilet and I release the latch. That's exactly how Oracle memory works by and large, in the same way that you would have access to a public toilet. Latch contention means someone has to wait. If this person on the left is accessing somewhere this memory and they're protected by this latch, this person on the right is now stuck waiting. They may have wanted to access a different piece of memory on this same linked list, but it doesn't matter. They're competing for the same latch. And it's what we call an active wait. It's not like we go and we say, oh, can I have the latch? No, okay, fine, I'll go wait for a while. The way we do it is what we call spinning. It's far too long in CPU terms to go to sleep and try again. That's an eternity in CPU time, even if it's only 100th of a second. So rather than going to sleep, what happens is when I'm trying to get a latch and can't, I do this. I just try again, and I spin. So what I'm actually doing is burning CPU. And as a result, what is that? Let's be very honest here. If you burn CPU on an expensive server, that is money, because you license your databases by the CPU. If you're running a database on the cloud, you pay effectively by the CPU. The more CPU you burn, the more money you spend. So latch contention hurts CPU, but it also hurts concurrency. If you're spinning on latches, you are getting nothing done. And that's the key. You're working harder to do less. At which point you think, when we talking SQL, wasn't this a SQL Fundamentals? So far you've spoken about servers, so far you've spoken about latching and memory structures. Well, to run a SQL statement, there's a lot we have to do. And to walk you through how to run a SQL statement at its very core, we have several phases. The first phase is syntax, which is, would this SQL statement run on any database? So if you look there, we can see I spelt from incorrectly. I did FRM0. No matter what database I have, whether it's Oracle, Postgres, Access, you name it, MySQL, that will never run on any database because it's syntactically wrong. That's the first check. Is it potentially a correct SQL? The next one is semantics. Semantics is, it's passed its syntax checks, but will it run on this database? That includes things like, have I spelt the table name and the column names correctly? In this case, I've got an invalid column name. Do I have the right level of privileges to access these objects, etc.? So it's syntactically correct. Now, will it work on this database? Then I have to work out how to best run it, and that's the optimization phase. In this case, it's come up with an index scan. Now that's the nice, pretty text tree picture we have. I then turn that into what we call row sourcing, which is effectively the machine version of that execution plan. What are the actual list of things I'm going to do? How am I going to read those index blocks? What files am I going to go to, etc.? That's coming up with a list of instructions out of how to do it from a machine perspective, how to run your query. And after all of that, finally we actually get to run it. And then we run our query, we actually go and access the disk or the memory. And if it's a select statement, we would then, for example, fetch from it. Now, there's a lot of preliminaries going on there: syntax, semantics, optimization, etc. We call it parsing. It's really the compilation phase. All of those things require lots and lots of memory access, which of course means lots of latching, hence my dwelling on the latching topic there at the start. Now, you might be thinking that's impossible to avoid, but we have two mechanisms that we introduced in Oracle to try avoid the cost of latching. The first one is what we call a library cache. And the library cache is simply a catalog of previously executed statements. I run a SQL statement, I incur all that cost of working out how to run it. But if you run the same SQL statement, then hopefully you'll be able to take benefit of the work I did. So I would parse something like this: select star from employee, etc. If it's already in the library cache, has someone else already run it? Well, then I know by definition the syntax must be correct. I know the semantics are okay. I can actually reuse the optimization information that the other poor person had to suffer. And therefore I can reuse the row source info. I can skip a number of steps and therefore get straight into avoiding a lot of that latching. So here are 11 random SQL statements. And if we walk our way top to bottom, we can see that the two orange arrows are our chances where we stumbled across a SQL statement that had already been run, and therefore we could actually avoid that parsing cost. We managed to avoid two of them. At which point you're probably thinking the probability of reusing the same SQL statement is probably low. If I'm looking up an employee called John, you're probably looking up an employee called Sue. Why would we share the same information that often? And, for example, here, we have a lot of different SQL statements in an Oracle database. But some SQL statements are actually nearly the same. And what we mean by nearly the same is the SQL statement is almost identical, except for just the value of certain parts of the predicates. We call them the literals. In this case, two queries, they're both looking for the same column, surname and first name. They're both from the same table. They're both using the same lookup, the employee number. All that's different is the particular employee they're looking up. Probably we would use the exact same optimization path if that's a primary key lookup. The syntax and semantics are all identical. So we have this concept of what we call binding to take advantage of this nearly the same style of SQL statement. We can parse this. We can say, here's a SQL statement without the explicit literal value. We use what's called a placeholder or a bind variable. We will parse that, and we will remember the representation of that, the row source information, the plan, etc. And then we can reuse all that parsing information for any value of that question mark, whether employee 1, 2, 3, 4, 5, 6, etc. Repeating those exact same 11 statements now, but with using placeholders or binds, we see the probability of reuse jumps up. It went from 2 full parsers to now we avoided 5 full parsers. We're taking advantage of the fact that applications often run the same SQL statements just for different literal values. Let's look at a demo of the benefits of doing this. I've got two Java programs here. We'll start on the top one. All I'm doing here is you can see I'm building up a SQL statement. Did I underline these? I did. I'm building up a SQL statement at the top here using string concatenation. If you're not a Java person, the plus is string concatenation. Because I'm concatenating this literal value of obj, this will actually dispatch 10,000 different SQL statements to the database. Each individual one will need to be parsed because it has a different literal value for object number. The example below will parse this once using a bind variable, and then we'll still run 10,000 executions, but we'll take advantage of parsing it once and executing it 10,000 times, each for a different value of object number. So the work done is the same, but the parsing costs will be much higher in this first one. Let's see what the difference is. Let's see if I can spell correctly. So we're creating a test table. We're doing 10,000 individual queries. Each one has to be parsed, and they're very simple queries. I did 10,000 queries. It took me, 6.7 seconds, which gave me a throughput of about 1,500 per second. As I said, even with parsing, machines are dramatically quick nowadays. Let's compare it now to binding. I parse once and then execute 10,000 times. The exact same 10,000 SQL statements, and you can see the difference is spectacular. I've gone from almost 7 seconds down to less than a second. I've gone from 1,400 per second to over 10,000 per second. In the old days when I used to do this demo on slow servers, the difference was profound and people would say, oh yeah, that's very impressive. The wow factor's sort of gone a bit nowadays because even in the bad example, I'm getting 1,500 executions per second. For a lot of people, they go, hey, that performance is fine for me. I'll never run more than 1,000 SQLs per second. Why would I bother writing that extra code for binding? Let's make it real. That was just a one-line SQL statement that had to be parsed. We generally don't do that in our applications. We start having joins, we have views, we have synonyms, etc. So here's a couple of database dictionary views, and I'm going to do the same thing. I'm going to run this complicated SQL statement with a literal value, as you can see here, and then I'll replace it with a parsing equivalent as we saw in the previous demo. So let's make it a bit more real world now in terms of how applications really have SQL. So this one takes a parameter, which is how many executions I'm going through. I'm just going to do 10 of that more complicated SQL, only 10. Now we start to see the cost, the true cost of parsing. Now I've gone from 1,500 per second down to 5 per second for 10 executions. And if I do 20 executions, it doesn't get any better. It's still going to be 5 per second. It'll take twice as long, about 3.7 seconds. Oh no, even long, only 4 per second now. 4 per second isn't that crash hot. That's pretty average. Okay, let's replace it with binds now, just to do 20 executions. And it's instantaneous. Now, you might be thinking, well, I've gone from 4 per second to 80 per second. That's 20 times better, which in itself is profound. But in reality, that's only because I only did 20. Let's make it 2,000 now. Now I'm getting 4,300 per second. Let's do 20,000. And you start seeing what the genuine difference is. I've gone from 5 per second on a complicated SQL to 5,000 per second. In reality, when you are doing parsing of heavy-duty SQL statements, you might see a 1,000 times degradation in performance because you're not using bind variables. That's hopefully a much more wow factor for you. Even after all of that, you are not convinced by the performance. This is much, much more serious. If you are building SQL statements by concatenation, like that, you're going to get hacked for sure. Guaranteed. Because if you're expecting on a SQL statement like this at the top for someone to provide you an employee number, this is what you're expecting in green, that they're going to provide you just a set of digits. But if I was a hacker, I would do this. I would say 6543 and 1 equals 0, which eliminates the top part of the SQL, and then union all, and then this. I'm looking for a table in your database dictionary that has the word security in it. If I find one called, say, app security, this would be the next query I run. 6543, 1 equals 0 to eliminate that. Union all, let's go looking for usernames, etc. A lot of us think that hacking is done by very sophisticated people when they come from countries far, far away. And I'm not picking on any particular country, I just picked a place that's a long way from Australia. And that, they have these, we've seen the movies where they have incredibly sophisticated tools, etc. Oh, I might need to reshare my screen here to share my computer sound. There we go. There we go. And it's not just us that think that, right? Here is literally on today's news, right? Have a listen to this.
Nobody gets hacked. To get hacked, you need somebody with 197 IQ, and he needs about 15% of your password, right?
That was literally on the news feed today about, what kind of person is qualified to be a hacker.
Nobody gets.
No, that's incorrect. Sorry, Mr. Trump. You can get hacked super easily if you're building SQL by concatenation, because the number one hacking app out there isn't some sophisticated tool that's used by the CIA, etc. It's Google. All you need is a browser. Now, in Australia, in fact, most places around the world, it's illegal to hack a website, so we won't do it for real. These are just some screenshots, and I've blurred out some appropriate things. But literally, you go into Google, you type in a specially crafted search string. The list of sites you get back as a result is literally a list of potentially hackable sites. It's like an advertisement. Hi, we're hackable. I go pick one. I go to their website. I've blurred out who it is. And all I do is add some special edits to the URL. If when I submit that URL, it crashes their site, in this case it did, I know they can be hacked with SQL literals. And in fact, this site was even generous enough to tell me, we're using MySQL, by the way. So now at this point, I now construct very, very elaborate URLs. Now that's obviously tiny, but if I zoom in a bit, what I'm actually doing is, in that same way as I said before, constructing a SQL statement on the URL to go looking for intelligence in their database. Now, constructing these is probably where you're thinking, well, this is obviously where all that, that 197 IQ comes in, that, the hackers have to have. Well, no, because there are freeware tools that do it. You literally go to a site, you type in the URL that you want to hack, and you press the go button. And what it does is it says, okay, it goes and works out what database you're on. It goes and tries to find out what data dictionary information is there. And then you simply click Get Tables. And it goes and gets all the tables. And every single one of these is an incredibly long URL that it's sent across the line to data mine the data dictionary. You pick some tables you're interested in, and you pick columns. So I picked a security table. I found 2 columns called password and email. When I've done that, then I just click on the Get Data. And it goes and finds a list of passwords and emails. Literally, Google and free software tools can hack you. Now, before you panic, that particular site demo we saw there was actually a site that's publicly put available by this guy, Troy Hunt. He's a security researcher here in Australia who actually lets that site be hackable out on the network so you can do demos. It's not a real site that we hacked, just covering myself here. But yeah, he's got a great blog showing you how easy it is to hack a website. It literally takes 5 minutes to hack you nowadays. These kids are 12 years old. They hacked their entire school district, not being malicious, just for fun. And that shows you how easy it is if you're not secure. You might be thinking SQL injection is a solved problem. This is a question I was helping out with someone on Stack Overflow. Same thing. What are they doing? Building SQL by concatenation, July 27th, 2020. And I haven't updated this slide. There was one recently just in the last couple of weeks as well. So if you want fast and secure SQL, make sure you always bind user input. It's so critical. Now, whilst we're talking about binding, as I said, we parse a statement. So we have this thing here. And it might already be in the library cache. So we know the syntax is correct. We know the semantics okay. So that means, right, that we can reuse the optimizer info, etc. Well, maybe not. We might still have some parsing to do. It's called soft parsing. And the difference here is a hard parse, you must do all of this stuff. Syntax, validity, optimization, etc. A soft parse means we can skip some of this, but we might still need to do this. Now, why would that be a potential cause here? If you find some SQL in the library cache, why would you have to still do some extra work? It's these kind of things that might create this. Scott logs on and runs this query. Mike logs on and runs the exact same query. So he will find it in the library cache, Scott having done the hard parse. But just because the SQL is identical doesn't mean everything is, because what if Mike has his own version of the employee table? Therefore, the Scott.employee table and the Mike might be totally different. The same SQL statement might point to different objects. Even soft parsing, while vastly better than hard parsing, still needs memory access and therefore needs latching. So can we do better? Is that something we just have to live with? Well, let's go back to the definition of a cursor. A cursor is, give me some memory, use that memory, here's your memory back. Now, a SQL statement goes into the library cache and it's shareable, and your cursor points to that. So the moment I close my cursor, I've lost that pointer. The next time I see that piece of SQL statement, I have to go look in the library cache and just double check that it actually matches all my objects, etc. That's the soft parse. So the next time we parse, we're guaranteed to have a soft parse just to make sure that that SQL statement is the one that is going to be useful for us. It sounds impossible to avoid, but what if we don't close the cursor? What if our program, for every SQL statement it runs, simply has a cursor pointing to it, and when we're finished with that SQL, we still keep that pointer? So rather than coding stuff like this, which is prepare a statement, run it, and then throw it away, we do this. If it's the first time I'm ever running select star from emp, I'm going to do all the normal stuff, parse it, etc. Otherwise, the next time I want to run select star from emp, I'm not even going to prepare the statement. I'm going to simply reset my cursor pointer, which is something you can do in Java, and it'll reuse that same cursor. So I never ever close a cursor. So if you don't close the cursor, what you do is you're hanging on to that pointer to the library cache, so you know that that SQL statement is perfect for you. You don't have to soft parse. That means, of course, your program must remember an explicit list of every cursor you've ever used and reuse them whenever possible. Now, if you have 10,000 different SQL statements in your program, you probably can't hang on to every single one. You'd probably run out of memory. So you need some mechanism actually of throwing away the oldest ones, hanging on to the newest ones, etc. What if someone comes along and drops the employee table? You need some mechanism of making sure that all those cursors that you currently have pointers to that point to the employee are aged out or invalidated, etc. So it sounds complicated. Yes, there's a lot of value there, but it sounds pretty complicated to do. But luckily, there is a free solution that will handle all of it for you, and it's called PLSQL. People often think that PLSQL is just something of avoiding network latency, which it is, but it's far more than that. Every static variable you use in a PLSQL program for SQL is automatically bound. So there's no chance of SQL injection. You've ticked off the security box just by using PLSQL. But more importantly, every SQL statement will hold the cursors open, even if you close them yourself. If you have a program like this in PLSQL, which does open this cursor, fetch, and close, the opening part will put that into the library cache, have the cursor pointer, and guess what? When you say close, we just go, you didn't really mean that, and we simply hold the cursor open. So PLSQL is the easiest way of getting even an elimination of soft parsing. So that covers part one, the compilation phase. Luckily, part two is much, much easier. How do we get and store results fast? And getting and storing is pretty much all programs do. Java, Python, doesn't matter what language you're using, all they do is put information into a database or get information out. That's all they do. And let's start with reading data. To query data, data is not stored in rows in the database. From our perspective, it is, but on the database, it's stored in blocks or pages, depending on what technology you're using. So to read data, you read blocks, and those blocks come from a data file originally into memory, so they're nice and fast, and then they go to you. But if it's going to memory, it's going through database memory, it's complex, and when we have complexity in memory, we have all these things floating around. What do we have to do? We have to latch. So even the act of reading data, not parsing SQL, reading data requires latching. And a typical program that fetches a row needs to do something like this. Get a latch so we can safely search along a list of data blocks in memory, find the block we're interested in, find the row in that block we're interested in, and then release the latch, give the row back to the client. When you want to fetch lots of rows in a cursor loop, fetch, 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 we get lots of latching. Your typical program looks something like this in Java, execute the query, and then loop around fetching. And what do? Get the latch, walk along the list, get the block, find the row you want, release the latch. Get the latch again, walk along the list, probably get the same block because it's part of the same table, get the second row, release the latch, etc., etc., etc. A better strategy is a thing called pinning. Now this is a bit of a long-running demo, so I'll start it now. Is pinning. What pinning is when you fetch a row from the database, you have a conversation. You say, by the way, I'm going to be fetching lots of rows. Just letting you know that. And the database can take action. It'll get the latch, walk along the list, get the block. It'll put a pin, like a little flag saying, Connor is here, please don't touch me. Now I can release the latch because my pin's in there saying you're not allowed to manipulate this block, and I can spend time in that block. Get the first row, get the second row, get the third row, all the rows that match my criteria in that block. Then I get the latch, remove my pin, and release the latch. So only a couple of latch acquisitions for lots of rows. But how do you tell the database, I want lots of rows? Well, it's the responsibility of the client. The database doesn't know automatically. So here's a typical Java program. There's the select statement it's doing. It's a query that's going to return lots of rows. There's the fetch processing. It looks the same. Looks like it's doing one row at a time. But the way you convey the information to the database is this thing called set fetch size. And the command you use is different depending on what language. This is for Java. There's things for .NET. There's things for OCI, etc. In this case, I'm passing in a parameter from the command line to nominate the fetch size. Let's go back to my demo. So I set this one running because it takes a while to run. I did 5,000 rows, but I'm fetching them one row at a time. And it took 30 seconds, which is still pretty good for 500,000 rows. But let's do it 100 rows at a time, the pinning concept. Now I'm down to 670 milliseconds. Let's do it 10,000 rows at a time. Look at this, the throughput on, once again, $900 machine, I can get 1.8 million rows per second out of a cheap piece of gear like this. It's mind-boggling how good machines are nowadays. So if you focus on blocks, we're trying to get the benefit of pinning on a block, and focusing on round trips, we get those performance benefits. Now, there's no such thing as a free lunch, as we say here in Australia. If I'm fetching 10,000 rows, or all the rows at once, all 500,000 down into my program, they've got to be held in memory. If I run it just in PLSQL, not even in Java, if I run it one row at a time, it's 70 seconds on this particular old machine. If I do it all with one big hit, yes, it's 8 seconds, super fast. This is an older machine, but I now have 500 megabytes of memory sitting around in my PGA. That's going to kill your server. There's law of diminishing returns. Remember, we're focusing on blocks. If I pin rows just on an 8K block, there's probably no more than 100 rows on an 8K block. So even if I get it just in batches of 100, I still get those great performance benefits, and I don't use anywhere near as much PGA. One of the cool things with PLSQL, again, is if you code your for I in cursor, for I in SQL statement, we automatically optimize that to being 100 row batches, and therefore we get the same performance benefits as well. Last bit now, storing data fast, the same rules apply. Think about sending data in batches when appropriate. If you're storing just one row, obviously send one row. If you're storing bunches of rows, send them over in batches. This is our last demo, and then we'll wrap it up. So this one's going to insert 10,000 rows, one row at a time, and it takes about 3 seconds. Let's now do 10,000 rows. I think this one's hard-coded in batches of 100. So 10,000 rows, but I'm doing in batches of 100. And you can see it's dramatically quicker, 44 milliseconds. But let's do 100,000 rows. Let's do 1,000,000 rows. Look at that, 1,000,000 rows in 700 milliseconds. This machine can store 1.5 million rows into a table per second. So let's summarize. If you want slow, insecure, crappy applications, don't bind them, don't read your SQL, and don't use any pinning benefits in terms of fetch size and batching. And the corollary obviously is, or the converse is, if you want fast, secure SQL and hence fast, secure applications, always bind your user input, always use pinning and array processing where appropriate, and you'll get these incredible results from cheap hardware and even better results on autonomous. So we've just slammed through a whole stack of slides. If you like lots of slides, I'll be back here on October 30th at 2 p.m. Australian Eastern Standard Times to talk about partitioning, all the cool things in partitioning. But at the moment, we're done for this session. We've finished pretty much bang on time. If you have any questions and you don't want to put them in the Q&A, or you want longer answers, please just reach out to me on Twitter. Throw your questions there on Twitter. Follow me on Twitter and hit me with a direct message. My direct messages are pretty open. And yeah, and we'll see and answer any questions that you had. But yeah, for now, hope you enjoy the rest of this conference. It's a fantastic event that Francisco has put on. We got over 100 sessions and 100 speakers. So please, make sure you stay involved in some all the other events as well. And I'll see you on the 30th, if not before. Thanks, everybody.
Thanks, Connor, and thanks everyone for joining today's session. And do not forget to register for the rest of the sessions. Hope you have enjoyed the sessions, and the recordings will be available on the playback sessions. Thank you so much and have a great day. Thanks, Connor, to you as well.